Section 18.5 now explores that relationship between Gibbs energy and temperature. The temperature is right there, and we can assume that the delta H naught and the delta S naught values, they do change with temperature, but we'll assume that those changes are small enough that we can just use our delta H naught and delta S naught values from that table of data collected at 298 Kelvin, and we can apply them in this equation over a wide range of temperature values. And we looked at an example in the last section of a reaction which was spontaneous at low temperatures but non-spontaneous at higher temperatures, and so you can start to get a feel for how there's some interesting patterns that might be emerging from this equation here. So if we look at figure 18.7, here we have four curves that are describing four different types of reactions. If, for example, delta H is greater than 0, so that is an endothermic reaction, the delta S is less than 0, so this is a reaction that has products which are lower in entropy than reactants. We can actually call that an exergonic reaction, but we don't use that term often. Then it will start with a delta G greater than 0, even at, in this temperature axis here, the x-axis, the temperature, it'll start at 0, at absolute 0, and then increase as you go to the right. And we're not giving you numbers here, but temperature can go forever. So let's say that the left side here is 0 and the right side is 10 billion Kelvin. An endothermic reaction with delta S less than 0, it will start non-spontaneous, and then as the temperature increases, the magnitude and the effect of this second term with a negative delta S times the negative of the temperature, well, that's just going to drive delta G naught even higher. And so it will become even more non-spontaneous at higher temperatures. We can look down here at the yellow curve, that's the bottom curve. This would be an endothermic reaction. Oh, sorry, exothermic reaction. Can I pause a minute? Did I say that backward the first time? This is an endothermic reaction where delta H is less than 0, that is non-spontaneous at 0 Kelvin. So a delta H less than 0, now this is an exothermic reaction, and at 0 temperature the only factor that matters in the equation is the delta H, and so it will be spontaneous because the delta H is less than 0, that makes the delta G less than 0. But if we increase the temperature for an exothermic reaction where delta S is greater than 0, then this second term is going to be negative. The negative T times the positive delta S naught is going to drive delta G naught even lower and lower. And so those will always be spontaneous. And then we've got these two blue curves that are in the middle. This one here is an endothermic reaction. Oh, sorry, I'm reading the wrong one. Yeah, this is an endothermic reaction for whom delta S is greater than 0. So this has more entropic products. And that will start non-spontaneous at 0 Kelvin, but as the temperature increases at some point, it will cross over. And we don't know where that point is. Maybe it's really cold. Maybe it's at 6 Kelvin instead of 0 Kelvin. Or maybe it's at 4 billion Kelvin. We don't know, but there will be some threshold temperature above which the reaction becomes spontaneous. And then finally this lighter blue curve, this is an exothermic reaction but it is also exergonic, and it's going to have a delta S of less than 0. And so as the temperature increases, that delta S term, which is positive overall, is going to grow larger and larger and larger because it's multiplied by that increasing temperature. And eventually it will cross over. There will be some threshold above which the reaction becomes non-spontaneous. Okay, so I actually like to represent this in a slightly different way than your textbook. It's the same idea, but I like to draw a sort of a quadrant diagram, and we'll put delta H naught up at the top here, and we'll put delta S naught over here on the side. And delta H naught can be positive or it can be negative. So these are endothermic reactions and exothermic reactions. And delta S naught can be positive or it can be negative. And so these are exergonic and endergonic reactions. If we think about it, a negative delta H, that tends towards spontaneity, and a positive delta H, that tends toward non-spontaneity. And a positive delta S, that tends toward non-spontaneity. A positive delta S, goodness, I'm glad I pointed that out. I was backward, forgive me. A positive delta S tends toward spontaneity because it is multiplied by the negative of the temperature, and temperatures are always positive valued. That makes this negative overall. And a negative delta S tends toward non-spontaneity. Okay, well, you don't need to write all of this up here on your own version of this. What's really important is what we put here in the corners here. So if I have a positive delta S and a negative delta H, then this is spontaneous at all temperatures. That's going to start spontaneous at 0 Kelvin because of the delta H, and then as the temperature increases, it will only become more so. Over here, we have non-spontaneous at all temperatures. If I have an endothermic reaction that is also, I've been saying exergonic, that's actually referring to Gibbs energy. I should say an endothermic reaction which is exentropic, then I'll just not use those terms. I'll just say delta S is negative. Then that will be non-spontaneous at all temperatures. So it's non-spontaneous at 0 Kelvin, and then it only becomes more so as the temperature increases. And then these two are where things are interesting. So and if I have an endothermic reaction, it starts out non-spontaneous at 0 Kelvin. At 0 Kelvin, that second half of the equation doesn't matter, it goes to 0. And then as you increase the temperature, that positive delta S value will be multiplied by a large negative T, and that will eventually drive the delta G naught value negative. So this is spontaneous at high temperatures. There's a threshold above which these reactions become spontaneous, and below which they are non-spontaneous. Then in this corner, we have kind of the opposite. This will be spontaneous at 0 Kelvin by virtue of its exothermicity, and then as the temperature increases, that negative value of delta H is going to undermine the delta H naught. Eventually it will overwhelm it and it will become non-spontaneous. So this is spontaneous at low temperatures. There is some threshold below which this reaction becomes spontaneous and above which it's non-spontaneous. Okay, now this is all you really need to know. And if you find it hard to relate these to that equation and to sort it all out that way, let me give you a common, clear example of how we can sort these out. Consider the melting of ice, the most intuitive and commonplace reaction that you can think of. Ice melts at low temperatures or at high temperatures. Ice melts at high temperatures, right? And now let's think about the energetics and the entropy of ice melting. Well, when you go from a solid to a liquid, that's a positive delta S. And ice melting, it feels cold on my hand because the ice is taking heat away from its surroundings. It's an endothermic process for ice to melt. And so that's a positive delta H. So ice melting lives in this corner. And I think everybody by the time they reach 3 years old knows that ice melts at high temperatures and that ice won't melt at low temperatures if you get sufficiently low. And then we can go the other way. We can say, what about water freezing? Does water freeze at high temperatures or low temperatures? Obviously at low temperatures. Water freezing is an exothermic process, and that might seem a little bit less intuitive than the ice melting example, but you can just say it's the opposite of ice melting. So if ice melting is exothermic, then water freezing must be exothermic. Or you can think about how if I have a big jug of water in the freezer, then that's going to prevent other things from freezing because because as that jug of water freezes into a giant block of ice, that's actually, it really is an exothermic process. It's going to prevent everything else from freezing because it's releasing that energy over the course of its freezing. Anyway, and water freezing to ice is going to be a negative delta S process. So water freezing to ice, that belongs right here. And water freezes at low temperatures. That's intuitive and easy for you. So anyway, hopefully you can kind of reconstruct this diagram. Even if you don't want to rely on thinking through that equation, you can think of that simple example of a chemical reaction of ice melting. Well, what about when delta G is equal to 0? When delta G is equal to 0, that's when you're right at the threshold between spontaneous and non-spontaneous. That's when the system is perfectly poised at equilibrium. So if I solve for that state, if I say delta G naught is equal to 0 at the threshold temperature, and solve for that threshold temperature, what I find is that T threshold is going to equal delta H naught divided by delta S naught. So we can find the threshold temperature, and then based on which of these is positive or based on whether these are both positive or both negative, we can tell whether that threshold temperature is going to be spontaneous above it or below it. And so let's look at an example, a familiar one. Right, our water formation from, oops, I shouldn't make that equilibrium. Our formation of water from hydrogen and oxygen. This is the example we used in the last section. And we knew that it had a delta H naught of reaction equal to negative 483.6 kilojoules per mole. And it has a delta S naught of reaction equal to negative 89.0 joules per mole Kelvin, and we can convert that into kilojoules per mole Kelvin, negative 0.0 4.89 kilojoules per mole Kelvin. And furthermore, we remember that it's spontaneous at those low temperatures. It was very spontaneous at room temperature. And then it was non-spontaneous at 5,500 Kelvin. So we know that somewhere in between those, it's got to make the crossover. Let's figure out what it is. What's our T threshold? It's going to be delta H, negative 483.6 kilojoules per mole, divided by delta S, negative 0.089 kilojoules per mole Kelvin. And our kilojoules and our moles cancel out, and the Kelvin survives in the numerator because it's in the denominator of the denominator, and everything works out nicely. We'll get a temperature in units of Kelvin. Let's calculate it. 483.6 divided by 0.0890. And it looks like it's 5,430 Kelvin. That is the threshold temperature. 5,430 Kelvin. Above that, the combustion of hydrogen gas becomes non-spontaneous under standard conditions. And below that, it is spontaneous under standard pressure conditions. Okay.